Welcome back, everybody. This is our solution for problem 3 from quiz 7. And finally, we have a series that isn't negative 3 to the n over 4 to the n plus 1. So this one looks a little more complicated, and the question itself indicates we have to work a little harder. Notice that it says use any tests, right? Plural. Any tests necessary to determine whether the following series converges or diverges. Now, there's probably multiple ways to approach this problem, so I'm just going to show you one possible direction. Doesn't mean you got it wrong if you did it another way, all right? So what am I looking for here? Well, the first thing I notice is that I have a polynomial on the top, a polynomial on the bottom, and then this nasty sine function that I really wish wasn't there. And so I'm just going to pretend for a moment that it wasn't. And so if I just focused on the rational function part of the sequence, I would notice, okay, I have a degree 2 polynomial in the numerator and a degree 3 polynomial in the denominator. Looking ahead, I'd be thinking, yep, I should be using limit comparison test on this, right? And all I'm going to care about in the end is the highest degree terms. And I'm not even really going to care a whole lot about the constants. So I'm really thinking about n squared over n cubed. Now, n squared over n cubed is the same as 1 over n, and the series for 1 over n, it's the harmonic series, it diverges. So from the beginning, that's my expectation, right? I believe that this series diverges. But there is this sign, right? And we want to see how that's going to affect things. So let's write down what we know about the sine function. So we know that the sine function is bounded. All right, it's bounded by -1 and 1. And if I take the absolute values, then, well, you can't get any of these negatives anymore. So the absolute value of sine of n will be bounded by 0 and 1. Okay, fine. Now I want to multiply by this rational function. And when I do, I realize, oh, wow, this feels really sad because there's this quantity here which is going to be negative. And at this point, I want to go and just pull this -1 out, all right? Because it's not going to change the convergence. So I'm immediately now going to pull a negative out of this numerator, all right? And then I will have just positive terms to worry about, which means when I multiply, it's not going to change the order here. So again, we have absolute value of sine on the bottom and this n cubed plus 6n plus 7. All right. So, and again, what I mean here, right, when I pull this negative out, right, is these two series, if one of them diverges, the other is going to diverge, okay? If one goes to infinity, then the other will go to negative infinity. That's all we mean here. Okay, cool. So now I'm going to multiply this sine of n. Oh, wait, but the sine of n's on the bottom. So I need to actually take the reciprocal. So what would that tell me about 1 over sine of n? Well, let's see. 1 over sine of n is going to have to lie in between 1 and infinity. Now, how am I getting that? Well, whoop, I didn't write it correctly, right? 1 over it. How am I getting it? Well, I'm inverting everything, okay? So inverting 1 is easy. Okay, this is 1 over 1. Inverting absolute value sine of n, fine, there we go. And then I need to invert 0, which really means I'm taking the limit of 1 over n as n goes to 0. All right, so, but I don't worry too much about this, right? What I really care about is that if the sine of n has absolute value less than or equal to 1, then 1 over the sine of n, right, the reciprocal, has to be greater than or equal to 1, which makes sense. You take a number like a half, you take the reciprocal, you're going to get 2. Okay, so this is the part that we're really caring about. And so now I can go through and multiply by this rational function. And when I do, I'm going to get 3n squared plus 4n plus 5 over n cubed plus 6n plus 7. is less than or equal to, all right, now the same thing, but also with the sign of n on the bottom. So 3n squared plus 4n plus 5 over the absolute value of sine of n times the quantity n cubed plus 6n plus 7. Okay, and again, this will be less than infinity, but that's not the important point. The important point here is we have now found a lower bound for our sequence. All right, and this lower bound no longer has the sine of n term in it. This is going to help us use the limit comparison test. All right, so what we're doing here is using now the comparison test. Okay, so by the comparison test, okay, what does the comparison test tell you? So comparison test, the comparison test is going to tell you that if you have eventually, so if you, well, let's write down, so you have a couple of sequences, an and bn, which are eventually non-negative. And in our situation, right, so the an is your original sequence and the bn is your replacement sequence. So this is my original sequence and I want to replace it with this sequence. And so if we know that the replacement sequence has terms which are beneath the original sequence, and if the replacement sequence diverges, just say it like that, diverges, then this implies that your original sequence diverges. So if you are bigger than the divergent replacement sequence, right, then when I say divergent sequence, I really mean the sum sequence here, of course, right? So if in both of these, right, if we know, right, that the series for Bn diverges, then the series for An will diverge because the series for An is just bigger than this divergent series. All right, so by the comparison test, if we can show that the series for 3n squared plus 4n plus 5 over n cubed plus 6n plus 7 diverges, then we will know that the series for our original sequence, 3n squared plus 4n plus 5 over the absolute value of sine of n times n cubed plus 6n plus 7, we'll know that that series diverges. Which was, remember, that was our initial guess. So we've reduced the problem to looking at this simpler series. All right, and as we had said at the beginning, all right, and you might notice that the -1 is gone, right? But this isn't going to change, right? Whether or not the series diverges or not. Okay, so at this point, we want to use the limit comparison test. All right, so I want to replace this sequence with the sequence 1 over n. So here's the claim. My claim is that the sequence 3n squared plus 4n plus 5 over n cubed plus 6n plus 7 is asymptotically equivalent to the sequence 1 over n. And remember, the way I got this was by, well, ignore all the lower terms, right, or lower degree terms of n. Just look at the top one and even just ignore the coefficient. N squared over n cubed is the same as 1 over n. All right, now it's a claim. Let's give it a proof. So we take the limit as n goes to infinity of the nth term of this sequence and the nth term of the sequence on the right. All right, and I'll take the quotient. So I have 3n squared plus 4n plus 5 over n cubed plus 6n plus 7, and we're going to divide by 1 over n, which is the same as multiplying by n. Okay, when I multiply by n, of course, in the numerator, that's pretty easy. I'll get 3n cubed plus 4n squared plus 5n. All right, so that's what that numerator is going to equal. And I'm going to factor an n cubed out of both the numerator and the denominator. So this will be the same as the limit as n goes to infinity of n cubed times, and what's left over? I'll have a 3 plus 4 over n plus 5 over n squared. In the denominator, I factor out an n cubed, and I'll have a 1 plus 6 over n squared plus 7 over n cubed. Now, because n is going to infinity, it's definitely not 0, so I can cancel these n cubes. So now I'm just left with the limit as n goes to infinity of 3 plus 4 over n plus 5 over n squared over 1 plus 6 over n squared plus 7 over n cubed, which is fantastic, right? All of these sum n's that look like something over n or something over n squared or something over n cubed, they're all going to go to 0, right? The numerators are constant, bottom is going to infinity, so they all go to 0. And so the limit is actually just the 3 over 1, which is 3. And 3, check that. Yep, 3 is definitely positive. All right, so this tells us we can use the limit comparison test. All right, because we have just established that these two sequences, again, because this is positive, these two sequences are asymptotically equivalent. All right, so by the limit comparison test, the series corresponding to 3n squared plus 4n plus 5 over n cubed plus 6n plus 7 diverges, that's what we want to show, if and only if, so if and only if the series corresponding to 1 over n diverges. Okay, so one thing to remember, in order to use this limit comparison test, yes, you need two asymptotically equivalent sequences. You also need them to be eventually positive. Of course, everything here is positive, so there's no question about that. All right, so we've reduced the problem from the original series, right? We wanted to show that this original series that had actually even a negative in it, there we go. We ignored the negative. We really just pulled this out of the numerator. We said, okay, we just need to show that this series was able to diverge. However, we could then use the comparison test to get rid of the absolute value of sine, because if you get rid of it, you actually get a bigger series. Then we use the limit comparison test to replace this underlying sequence, which is this complicated rational function, with this very simple rational function, 1 over n, right? This asymptotically equivalent sequence. And now we just have the harmonic series, right? So, but this is the harmonic series, which diverges. Okay, so we could use that general knowledge there, or alternatively, we could say diverges by the p-test, because this is a p-series where p is equal to 1. And recall, if you have something of the form 1 over n to the p, that series is going to converge if and only if the p is greater than 1. So as soon as p is less than or equal to 1, the series will diverge. So there we go. We have proved, thus, the original series, which, who can even remember what it went from? Let's see, was it 1? Okay, fine. N goes from 1 to infinity. Negative 3n squared minus 4n minus 5 over the absolute value of sine of n times n cubed plus 6n plus 7. That original, just silly series diverges.